Hey everyone, welcome to another episode of RoboPapers. Super glad today to have Haoyu Xiong with us. He's one of the authors of this paper called Vision in Action, Learning Active Perception from Human Demonstration. Thank you so much for making the time, Haoyu. Maybe as a start, if you can share a little bit about yourself, that would be great.
Yeah, thank you. Thanks for having me. Hi everyone, my name is Haoyu Xiong. I'm currently an incoming PhD student at MIT EECS. Before I joined MIT, basically I was working on real-world robotic systems. For example, this robot neck project. And previously, by the way, this work was done at Stanford during my visiting with Professor Shuan Song. Before that, I was a master student at CMU working with Deepak Pathak, where basically I worked on several projects like mobile manipulation and some like teleoperation for text hand manipulation, quite a few real world robot system, and I quite enjoy them. And today I'm going to share you some of our latest research about why do we need a robot neck. Yeah, thank you.
Okay, awesome. Yeah, so if you can just share screen. I know you have some slides.
Okay.
Yeah, we can just go from there. Okay, perfect. Yep, we can see it.
So the title is Vision in Action. Like basically, vision is like action in your policy action space. And okay, let's get started. So I guess the first question of the entire project is, why do robots need a neck? If you look at everyday activity of human beings, for example, if you want to insert something, a fixed camera view is just insufficient. Oftentimes, you just need to naturally adjust your eyes view or your gaze, and oftentimes you just don't realize that. And another example is like for mobile manipulation, maybe a fixed head camera is insufficient if you want to grab something inside a container. So we do believe that for a lot of visual occlusion scenarios, a moving camera, actively moving camera, is essential for manipulation problems. Another motivation of this project is like, I guess many of you know, like, for example, Aloha, Umi, a lot of data collection systems nowadays, they do not use active egocentric cameras. Instead, they use wrist cameras. But there comes like a very fundamental issues is what the human sees compared with what the robots learns from. For example, your wrist camera, what you recorded, or what the robot sees. There's like a fundamentally mismatch. Imagine human eyes can see quite a lot, but oftentimes maybe the wrist camera has already been occluded. But as the human teleoperator or the human data collection expert, you may not know that. And the recorded data may contain some like noisy information. And here's an example. This is a robot that we built. Imagine if you just have two wrist camera in this bagging searching task. We found that at a certain moment, your wrist camera are gonna be completely occluded, and the information you captured is just like useless. For example, right, like the left hand wrist camera could not see anything, and the right camera also does not sense any useful information. Now we have to have like a active camera and a robot neck to adjust their camera pose to gather task relevant information. For example, this task, we want to grab a banana in this bag, and you just have to find a certain camera pose to get the task relevant information. Now we call this see what the robot sees. I think this is kind of a missing part in today's data collection paradigm. But I think I'm really glad to see many concurrent work or some prior work already trying to develop and pay attention to this see what robot sees, like align human observation with the robot observations. So
I like the hat a lot.
yeah, thank you. Yeah, that is just
Yeah, I was gonna say like that really helps to tell like which is the head, which is the head.
yeah.
I did want to ask, there's a chest camera. Are you using that as well?
Oh
Just the
yeah.
one on the.
So
Okay,
that is for ablation study. So when we
makes sense.
collect data, we open every camera streaming up. So that is like a fair comparison. And this video demo show an example of if you don't have a neck, for example, if you pay attention to here, and here's a wrist view. At a certain moment, it's completely occluded. And some other people might ask, maybe if you have history information, you probably know where the target is, right? Even though at a certain moment it's occluded, but it's not always occluded. But I think in realistic environment, what if the object is like a dynamic object, right? Like what if the scenario is more complicated and the object is moving around? I think in such cluttered environment, visual occlusion is really a challenge, and we need to have like active camera instead of just like a race cam, because oftentimes race camera, their motion is constrained by the manipulation needs, not driven by the perception objectives. That's why, yeah, I gonna tell more about how we build this system and how we deal with those visual occlusions. Before we talk about the how we collect the active perception strategy data collection, another motivation of our system design is many people might curious, why do you need a six-stuffed neck? It looks just so creepy. It doesn't look like a human being or humanoid. Actually, I would like to share a little bit about this the story behind this project. At the very beginning, I was proposing to my advisor, Shuan, like I was like, I want to design a robot neck. I want to have like an open sourced hardware project, and many, for example, Unitree G1 humanoid, they don't have a neck. Maybe they can use our open source project. But Shuran was like, why not just use another arm? Although it's not a new idea, but she thinks it's just like simple. We don't want to spend too much time on the hardware and the control side. We want to directly dive deeper into the research direction, like just mount another arm on top of the bimanual setup. So that's a motivation one. And motivation two is like prior work. For example, there's like open television. I'm gonna talk about this very important prior work. Actually, many of our code is based on their project. But if you just have a two-dot neck mounted on like maybe a fixed torso, oftentimes it's insufficient, right? Because if you think about human being everyday tasks, we do not just use the neck. We use our torso, our body, sometimes even lower body to like whole body control your gaze. To maybe you have a very high cabinet or something like you need to bending down. That's why we believe that having a sex neck just give you a larger range of motion, and this can allows you to mimic human whole upper body motion to achieve more realistic tasks. Something I'm gonna show you later. And yeah, we just want to avoid complex hardware design. That's why like having three arms is basically a minimal humanoid. I quite like this simple hardware idea. So the next thing is, how do we control the robot neck, and how do we collect the data? So I really like this prior work from UCSD, from the first author Xu Xiong, and also his team. But this is also quite standard, let's say, first person VR teleoperation system. We also use teleoperation because it's just like a simple to set up and collect these active perception strategies. But it was not easy. So standard pipeline is like you have a robot, and perhaps your robot has like a onboard computer, and you stream your RGB camera, right? And your camera streaming RGB videos, or let's say RGB images from your camera to desktop, and using Wi-Fi to transform this to like a VR headset. There's like everyone knows that there's like a data transmission latency, but I think this is like a engineering problem, and many prior work, and this basically I think is solvable, and we can try to optimize the whole pipeline to make it really acceptable and make people feel much better. But another thing, many of I think the VR users may not notice is the control latency. So this is something new in robotic domain. Like in VR, perhaps we don't have this VR helpers to robot neck control. This control latency might come from maybe your robot controller code, or maybe your CAN communication, or maybe some of the motor latency. Like it's almost impossible to ask the robot to immediately execute your action commands, right? Like for example, here's the I just like slow down this open television video demo. If you slow down, you can find out that sometimes For example, when I control the robot neck, I already turn to another direction. For example, from left to right, the robot would not always immediately follow your action. It will somehow slow down a little bit. And this viewpoint mismatch is a fundamental issue to make you really motion sick. So if you had the experience to using such like a VR egocentric control pipeline, I guess many people will feel uncomfortable. I'm one of those, and that motivates us to think about how to come up with a really practical solution to first be able to collect a lot of active perception strategy data set before we dive into the policy learning part. Yeah, so how did we do this? We did not just use direct RGB camera control. Instead, we have a 3D, we call it like a 3D interface in between. But this is just like a simple point cloud in a word frame. So what we did is like we use iPhone camera. That's also one of our design choice. iPhone provides you really nice RGB, very accurate camera pose tracking. So you can just get a point cloud in the robot word frame. Meaning like no matter how you shake your robot camera, no matter how your neck moves around, the object will always stay still in front of you. And basically you just like bring this 3D thing from your robot real world to your virtual reality world. And what I really see is like a real time, really fast, high frequency rendering based on my latest head pose. So meaning like, although point cloud can bring you some latency, for example, the phenomena already happens. I already closed my gripper. Maybe this like event happening will still have a latency, but my viewpoint updating, or let's say novel view synthesis, is really smooth because you always see a viewpoint from your own headset pose, and this allows you to just get rid of motion sickness. I think this is really a cool idea, and this is actually not very hard to implement. We open source everything, and please try our code base and email me if you have any issue. And also, like another part of this teleoperation system is like we also need to control the camera pose and also sending point cloud back to the Vision Pro. And this part is like updating asynchronously. And it's like a 10 hertz, but for the view rendering part, it's like over 100 hertz, and everything makes you feel comfortable and smooth. I do, and this is basically the idea of how do you disentangle human and robot head motion. I do want to mention here, point cloud also brings some limitations. For example, although I think iPhone gives you nice RGBD, but if you convert back to point cloud, you can see the points is always jumping and is much lower fidelity if you compare to RGB videos. I think in the future, if you have some perfect like 4D Gaussian selecting or whatever, I guess this could make their experience better. But here's just like a proof of concept, and we introduce the idea how you disentangle human and robot head motion.
Since you were saying you're accumulating head poses, does that mean that your point cloud takes like the point cloud that you're displaying? Is that the result of multiple accumulated head poses then? How does it handle like a dynamic scene? Does that make it harder to teleoperate the robot?
Yeah, so I think for very dynamic task, the challenging part is because the point cloud updating still has a latency, right? For
Yeah.
example, like the example I gave, I close my gripper. What I see when I see my, from the view the gripper is closed, there's like a certain latency, and this would somehow affect the dynamic task teleoperation performance. By accumulated head pose, basically I mean like asynchronous updating.
Oh, okay.
Yeah. We use the absolute human head pose in the human body frame and transform this to the robot frame.
Makes sense.
And this is basically updating asynchronously. Yeah. And here's a visualization of this whole async teleop pipeline. I can go through this again. Basically, you have these RGB observations and transform to the Warframe point cloud. And what you see is like a view rendering in a much higher frequency. And you use your head pose in a lower frequency to update the robot head pose and update the RGBD observations. And here's a, I guess, a video visualization. So as you can see, what I mentioned, like the RGB, the point cloud thing is a little bit noisy, I would say, and it's much lower fidelity. I think it limits its performance for some like fine grain manipulation or dynamic manipulation. But for our task, I think we focus on like visual occlusion. I think I'm comfortable to use this system and teleoperate. And another thing I would like to address here, as you can see, why we need sexed off neck. When I try to bending down my right, like this is actually quite challenging. You basically want to move your torso bending down to find a better view. And if you just have the two off neck, I guess basically you cannot see what's below this shove.
No.
Oh, okay. So this is actually
I think it's like a little stuck on
my
the
first
back.
time
Just shake around
when
a
we
bit.
just built this system. First time trying to grab something in this bag. As you can see, it's really quite challenging, even for television. And
Here,
I
yeah,
like
see
we
what happens.
recorded
Oh,
this
nice.
video, and you can see his background voice is really cute.
No.
Yeah, I tried my best to try to grab this out. Turns out it was not easy. And at that time, the system was not very ready. Yeah,
Wow.
successfully get this key from this
Wow.
equation scenario. Yeah, let's move on.
A little stuck.
To okay. Yeah, so here's some of the autonomous policy after we basically use this teleportation system to collect a lot of data. I would like to first give a overview of our design tasks and how the autonomous policy perform, and then we will dive deeper into the numbers and the results, some of my thoughts about like diffusion policy performance on this active perception setup. Yeah, this first thing is like I would like to introduce a little bit more about this task. So for the data collection, for the training data collection, for example, this target object is placed randomly under this occluder, and we also place this yellow cup on the upper side or the lower side randomly during data collection, meaning that at testing time, the robot has to first figure out where the target object is, right? It needs to first find the object before using the arm to go to the right section. And we found that some baseline failed to understanding and finding the object. And yes, another task is a back task. I think the challenging part is like you need to first use your gripper to open it, and during this deformable object manipulation, the target object inside the back might be randomized, like the place you don't know where it is. That's why you also need to like look around to localize it before grabbing it. And the third task, actually, this is a very challenging one. During data collection, we will first randomize this shelf. It is like a different configuration so that the target object would be like initialized in a very randomized 3D space. So you have to like first localize it. And we also observe some long horizon searching performance is quite interesting. Even with a very simple behavior cloning network, the robots learn to like look around. If it cannot find the object, it would not take any arm action. It will also move the arms unless they find and localize where the object is. And you can see it can use the right hand or left hand to grab the object based on where the object is. And for this stacking strategy, it's also a challenge because, right, imagine if you want to stack a part on a metal something, you have to find the alignment part. You have to basically slightly find a better view. A fixed camera oftentimes fail to do so. Yeah, let's move to the okay, let's move to the policy learning part. At the very beginning of this project, we just have we had an intuition that maybe word frame point cloud brings more robust spatial understanding, right? Like this camera is always moving, but if you have a word frame point cloud as your robot observation, the object would stay still. And we just wanted to do this word frame diffusion policy, and we thought it could bring us better. And this is also motivated by some of the prior work. For example, DexCap, they show during the data collection, a human body torso like moves around, and during the robot deployment, the robot camera is fixed. There's like basically a distribution gap. That's why they use word frame point cloud to bridge this gap. So we did the same thing. As I mentioned, the VR stuff is like a 3D word frame point cloud, and we use this as a diffusion policy input. But there's a very quite interesting thing, like DP3 does not demonstrate like a semantic understanding. For example, it always fails to find where the object is, and we found this never demonstrated in our RGB policy. It's quite interesting. So we guess that maybe all of those point cloud policy trained from scratch has some limitation of understanding like semantics or where the object is. And if you look back, I personally actually searched a little bit about all of those encoding representation study about point cloud, but it turns out PointNet is still seems like the best, although it's like quite a decade, I guess. And if you look at the, there's some like 3D lifting starting, like you can lift the 2D to foundation, like vision feature encoded features to a 3D space using the point cloud. But it has some like a computing issue, I think. But basically what I want to say is like, I feel like RGB encoding and representation is just better studied today. And I think like there's a lot of like RGB like videos in our internet data. So maybe it's a more scalable way. I'm gonna talk more about this in my following slides. So we just went back to RGB based policy. It was also nothing new contribution. I mean, from here, it's just like a ResNet, ImageNet pre-trained ResNet and Dino V2 pre-trained VIT as our visual backbone encoder, and we compare with those three visual representations. But we did find out that if you have a nice pre-trained visual priors, this can help you to understand like where the object is. And we have a very like interesting finding that RGB policy is always better than DP3. So, and I would say one thing I want to address, we are very confident about our rollout. And if you go to our website, everything is like our policy rollout is like uncaught, like 10 or 20 rollouts, just one time I recorded the numbers. I really like this demo video. Maybe let me play again. It's like, this is like our policy rollout, and we place the object randomly everywhere. Actually, we marked those testing locations. And you can see this VIT pre-trained visual prior just allows you to look around and find where it is before you moving your arms. And no matter you put it right side or left side, it's like always somehow be able to find it. And here's another really interesting finding capability videos during our rollout. So let's pay attention to this part. The object is somehow occluded by its own gripper at the very first frame, and the robot somehow moves the gripper a little bit and it finds it. But although it's like a failure case, it didn't successfully grasp the object. But I see this is like a very interesting rollout I collected during my policy evaluation.
Yeah. Do you think
Maybe.
it failed there?
Sorry?
Why do you think it failed there? Oh, why do you think it failed?
It failed maybe. I think it's just like didn't
Bad
go
luck.
to the right grasping position.
Yeah.
I killed it halfway. I spent too much time. Actually, it has a retry. And I guess this location might be a little bit OOD for manipulation side, but
Makes sense.
it's just luckily finds out. So this is a first part is we compare different visual representations, and the second part is we remember at the very beginning you asked the question why we have like multiple camera on the body. So we had such like a ablation study to answer the question: is the neck really necessary? So here's the example of the basically when you have the neck, and here's another example. So basically, we did not use the robot neck, and we did not use the entire thing, the iPhone camera. We used the 3 cameras from the chest and 2 wrist camera. And the training data set is the same data set, just different camera configurations, and I train the policy to compare with. And we do find that as I mentioned before, the occlusion things. We can double check this again. During those grasping moment, there's no camera that can sense the task relevant information. As a result, this like failed many times. And I think this is like quite intuitive to our hypothesis. There's another videos example of this grasping the bag. As you can see, there's actually we really carefully to design those tasks so that, as you can see, if you just have wrist camera and chest camera, sometimes you can see a little bit about the blue object. Oftentimes it's like occluded. As a result, it's like a field. As a comparison, if you can actively to gather task information, and this strategy is not just like from human demonstrations directly. And let's
So
go
how
to-
you? I have a question. So yeah, I guess are these similar videos? So when you do the policy with the neck,
Yes.
does it only have like the video input from the active neck, or does it also have wrist camera from both?
No, this one we don't have wrist camera. We have another ablation of adding wrist camera. I'm gonna talk about that later. Yeah. For when I say our policy or VIA policy, it only has egocentric active camera. And here's another example. If you do not use the active camera, you use this Aloha setup where you have a chest and 2 wrist camera. You oftentimes fail to complete this task. I would say this is quite challenging for like this visual occlusion design. Here's a visualization and also a figure in our paper that we recorded some crucial moments of the occlusion happens. And basically the finding here is like the baseline where you use just chest and wrist camera oftentimes fail to provide task relevant visual information, and as a result, it performs much worse than our policy. But yeah, to answer your question, why not add 2 wrist cameras? So for this baseline, basically we have 3 cameras: the active head camera and 2 wrist cameras. And we try to answer the question: do redundant wrist camera help? So I'm gonna show this table directly. This is actually a quite surprising result. And at the very beginning, my advisor was challenging me quite a few times. Like we did those evaluation again and again. We just found out having extra cameras actually makes the performance slightly worse. This is not very intuitive. So my hypothesis or my explanation is like, I think first of all, we do not have a lot of data. Every task is around like 150 or 200, 300 demonstrations. In such low data regime, I think having a noisy wrist camera input somehow maybe sometimes make it overfit to those noisy input and makes the performance just worse. And we tried, this is not demonstrated in my paper, but I also tried it using separate encoder for separate cameras or using a shared encoder for 3 cameras together, pre-trained or like a frozen or fine tuning. It's just like always slightly worse than just having a active head camera. And we also think that having active head camera is basically task complete, right? Because human expert can just using this view. And by the way, the VIT takes a cropped image as an input, right? It has to be like a square, and I also cropped it my VR view to make sure that the human teleoperator see exactly what the robot sees. Because I think human policy can finish this task. If your diffusion policy learns this strategy, it can also finish this task. But I would say if, let's say, in the future we want scaling up a lot of like AR glasses, human data, do we really need two other wrist camera? Yes and no. I'm not pretty sure, honestly. But from a budget side, I think as long as you recorded your active head camera motions and your egocentric human views is aligned with the robot, maybe it's just enough. But maybe if you do not have tactile sensing, oftentimes the local wrist camera plays as a role like a tactile. It might be useful at some sense. So I think they come to the end of this presentation. Some key lessons I think I would like to discuss and then learn is I really like my advisor's philosophy of keeping everything simple. I think because what we really want to study, actually we didn't have enough time to dive deeper of this active perception project. I think there's still a lot of scientific problems to be solved and to be researched. For example, some attention mechanism inside this active moving camera. But if we spend too much time on these hardware stuffs, I think we would have less and less time to dive deeper into the scientific problems. But don't get me wrong, I think hardware is actually a very important part to make the whole robotic system work. But I think I also see nowadays as a PhD student, there are actually many industrial startups. They are building hardwares and we can collaborate with them and they are building hardware basically for us. I think as a PhD, we really need to dive deeper into the research problems and the scientific problems and keep everything just simple. And second thing is like after finishing this project, I think we really need a neck. Neck is just makes the hardware not simple but harder and complex. And having a neck also makes the data collection a harder problem, right? If you ever try the VR teleoperation, I would say it's still not a happy thing to collect data with a Vision Pro or whatever. It feels really uncomfortable. For my setup, I personally can use like 3 or 4 hours. My longest record is like I guess 3.5 hours. I do not feel
Wow.
motion sick, but I feel really tired. So motion sick meaning like you are really disgusting or uncomfortable. But with this point cloud stuffs, I do not feel motion sick, but I really feel tired because the Vision Pro is very heavy. I see today a lot of people are interested in like AR glasses, egocentric data collection. I think that's a really interesting and promising direction. A lot of the prior research, they did not include this active camera action as part of the policy. I think in the following research, we really need these camera actions. So I think, as I said, VR television is hard to deal with and maybe it's hard to scale up. But how can we have a let's say comfortable, portable, and practical data collection interface? I think that's something interesting to look at. And I think the one last thing is like, for me, I am a strong believer in just like RGB policy can implicitly learn such 3D representation. Or maybe I can have 2 stereo RGB cameras. And we believe that RGB can just handle those active camera setup. When you have a lot of diverse camera pose data, a lot of massive data, I guess such like a 3D structured representation is not a big deal compared to using point cloud. And nowadays we have a lot of like foundation depth model, right? You can somehow infer depths and 3D stuffs from those pre-trained foundation vision models, I think. One more thing is like we are also quite interested in mobile manipulation stuff. I think in mobile manipulation there's a lot of like more interesting cases where you need active perception. And how do you represent your action space with active perceptions? Those are very interesting and open problems. We just didn't have enough time, but I'm quite interested in this future direction. Yeah, that's all for my presentation. Thank you.
Thank.
Wow, that's
Very interesting.
yeah. Well, thank you so much, how you I have a lot of questions, but I felt that as you talk, you answered most of my questions already. So yeah,
you.
that was a very comprehensive presentation, and I mean I mean the success rate is so much better with the active neck, and I'm also a little bit surprised that adding more camera doesn't help. But maybe because the sample size is still a bit low, but
Yeah.
I can also see maybe why. Well, but maybe okay.
Yeah.
I guess to your point, maybe like because we don't have sense of touch with these robots, so camera can maybe replace that a little bit. Maybe it can help in those instances, or like just I was gonna say occlusion, but I suppose if you have a six stops that can really look and lift up the thing and then look underneath, then you just do that. And yeah. Well, by the way, for the VR, sorry, Chris, yeah.
Oh no, I thought it was really interesting that the what you're saying about the 3D diffusion policies not helping, the 3D models not helping at all. Like that's so I guess maybe not so surprising because as you said, it's all web. Like, the RGB images are all you can pre-train them. They're very well understood, but it is, yeah.
Yeah.
Do you have any more thoughts about why that would be?
For the 3D diffusion stops, we also have another experiment we didn't show in the paper, is that for our training and testing scenarios, the camera pose is not completely OOD, right? Basically, during training, I move my head, and testing is the same thing. And we had an experiment where we collect the demonstration with a fixed camera pose. And at testing time, we just shake the camera quite a lot. The word frame DP3 works quite well, obviously, right?
Sure.
Because the object stays there. But the camera, obviously, it doesn't work because it's quite OOD. So I think it really depends on your training and testing scenarios. And I think if you have a lot of let's say I put on my AR glasses and record a lot of diverse data, RGB might be just okay.
Makes sense.
Yeah, I'm curious. Obviously you went through a lot of engineering work to make somehow the VR teleoperation bearable. I think 3.5 hours is crazy. So
yeah.
By the way, I mean I've been trying to kind of force myself to enjoy VR since the first Quest, like this is ages ago. I think I've puked twice before, by the way. So I actually threw up twice, in two different games. So I'm one of those that can quite easily get motion sickness. And over the years, I keep trying to force myself, but I just never quite get past that condition. So I completely get even just a little bit of latency. I feel that I sense it very quickly. So I can totally see why you have to do all that engineering work.
Yeah.
I'm curious.
Oh, sorry. I was going to say the motion sickness, basically, again, I want to double address is because the viewpoint mismatch.
Yep.
Oftentimes, why people get motion sick is because I already imagine I turned my head around, but the view is not updated on your display. Yeah, with our onboard rendering, this just get rid of this kind of view updating latency. Very interesting story I would like to share. At the very beginning, I was using MetaQuest. I just could not resolve these latency stuffs, but I just switched to Vision Pro without changing anything. And the Vision Pro just the rendering is just faster. And later I realized why Vision Pro is 6 times expensive than MetaQuest, because its onboard computing is very, very strong and powerful. And everything about this rendering is happen onboard. Yeah, that's why it's super fast.
Yeah, I'm wondering, I'm just speaking from personal experience, what do you call that? This is called yaw, is it? I think this is called yaw. As you teleoperate VR, do you feel that you, for certain tasks when you have to do this yaw motion, I don't know whether you actively try it, does the system react well, or basically, I guess, it doesn't make a difference, or you don't recall that at all? Because for me personally, when I do this yaw action, it always throws me up. Whereas if I turn like this, pitch and roll, it's actually quite okay.
I see. So for our setup, basically we use all the 6 stuff. So the rendering is based on my 6 stuff head pose. And the robot neck control is also 6 stuff. It just makes you natural. And as I mentioned, we didn't just do this way. We are basically doing this whole upper body way.
But you're displaying the world frame point cloud, right? That's how you get around this. Because if you were displaying it relative to the head, then that latency would cause most people to throw up, I think, right? Because there'd be a pretty dramatic latency, right?
Oh, sorry, I didn't get your question. Can you say that again?
this is a clarifying question. I think this is what you said earlier, right? So you're displaying a world frame point cloud.
Yeah,
so
yeah,
if I
yeah,
tilt
yeah.
my head, there's a latency of like maybe a tenth of a second before the robot gets to that position. It's not like what you're seeing is tilting or something like that, right? It's not like it's
Yeah,
displaying where the robot head is. It's like it's a point cloud, so it'll lag. So like there'll be a point cloud here. If I tilt my head, there'll be a point cloud here where the robot's actually seeing, and then and then it'll adjust, right?
Yeah.
Does that make sense, Mike? That makes
Basically,
it so that Sorry, go ahead.
Yeah, basically it's like you could imagine we are bringing the 3D scene of the robot world to your virtual reality world.
Yeah.
And the way to rendering. Yeah.
Got it. Yeah.
So,
So
you're
I
not
guess
seeing
like
like an image. You're not seeing the robot's
got it.
view from
Yeah.
that. You're seeing
Yeah.
like a point cloud that might lag.
Yeah,
And
you
I
are
think it's a
Got it.
really good idea.
Yeah.
It's a really nice way around this issue, honestly.
So yeah, basically the trade-off here is you at least you don't get me sick, but then you may show me something that is maybe a split second after the reality, but that's still fine. At least I didn't throw up, right?
Yeah.
So that's the
That
trade-off.
That's
Yeah.
the idea.
That latency part comes from the data transmission part. Data transmission latency, we did not deal with that part. That part actually is, I think by the way, like our code is also based on the Open Television code. I think Open Television already did some good thing about the data transmission latency. So that part is okay. Yeah, it's acceptable.
That's the one we try to mimic, Michael.
Yeah. I remember.
Yeah,
I was
okay.
I was quite surprised. Like I didn't.
I was
throw
really
up.
impressed by it.
I was
actually.
a little yeah. That was a really memorable demo. We were like both me and Chris. We tried the teleoperation. What do you call it? Open television, right?
Open Television.
And then it was like from Munich all the way to I think the board
San
was in
Diego.
San Diego.
Yeah.
I was like, oh gosh, like this is crazy.
Yeah, this is
I do have a I do have a follow-up question.
Go
You know, you mentioned about AR glasses.
Mm,
I mean, long term, do you think all these efforts that you try, you know, doing VR teleoperation so that like the humans can be in the loop, does it pan out like, or do you think it's just more straightforward just to use AR glasses? Yeah, what's your sense?
So all of those UMI, UMI data collection, recent like DEX UMI, or maybe like egocentric UMI, human data collection, I think what is it's definitely better to scale up in the wild to gather a lot of diverse real world data. I think I believe there are already some ongoing work on this direction, and maybe very soon we could see some new work. But I think teleoperation still gives you a very high quality data, right? Basically, you get what you teleoperate, and those data can directly train policy. You don't need to worry about, like, for example, human data collection latency matching to the robot hardware. I think if you read the UMI paper details, there's a lot of engineering efforts to make this work. So to conclude, both words are necessary, but I see at least in academic papers or the prior AR glasses papers, they did not use the glasses head pose. This is a missing part. I think there are one or two papers. For example, I remember UCSD Xiaolong's paper. There's like a humanoid policy, blah blah. That paper has the AR camera action as part of the policy. But for example, Ego Mimic, they did not use the AR glasses actions. Yeah.
I mean, the other problem is that
Sorry, Chris.
you need to know, like, if you're training active perception policies, which I think most people aren't, right? Like, if you're training active perception, then what the camera can see is really important, right? So, like, I feel like it's an interesting discussion, but like, how would you use AR glasses in that case if the sensors on the robot are different from the glasses? I think even the Mimic, they literally just put the glasses on the robot, so maybe that gets around it. But like, you have to be able to
But perhaps the other thing is also like these glasses just don't have nearly as good slam compared to
I think, from what I understand,
the Aria does.
Is okay. Yeah, Aria glass, the camera pose is okay. Yeah, it's not bad.
But like, if you can, right, if the task, so we have like peripheral vision, like I can see stuff that's directly over there, right? So even if the glasses are seeing forward, maybe like there's a huge difference in what the robot can actually see and use with glasses versus if it's like the headset has the advantage of actually blocking everything out, right? I don't know. So that you know that whatever the human is seeing is what the policy can see. I don't know. I think it's a to me at least, that sounds like a huge advantage of how you did, right? I mean, it just comes down to data quality, right?
Yeah.
Anyway, I don't know.
How many? I'm curious. Like how many? Like for a particular task, how many tries do you try for? Demonstration do you try roughly?
You mean how many demonstration do I collective
Mhm.
to train policy,
Mhm.
or do you mean
Mhm.
to make
Yeah.
to train myself first? Yeah, that's
Okay,
another.
I didn't even think about that. Okay. Oh, interesting. Also, to train up as a teleop. Okay, I see. To get
So
used to
I
it.
would say, yeah, I would say those tasks are quite challenging. So actually, let me share my user study tables to talk a
Yeah, that's right. Actually,
bit
you have this
more,
table that talk about motion sickness and then preference, right? I think,
and
yeah,
also
actually that.
how can they
Mhm.
like a common user like every result in my paper, the demonstration is collected by myself. I'm like a perfect like expert. But what about just like random
Yeah.
volunteers?
Mhm.
So let's go to this. Yeah.
Mhm. Yeah,
Actually,
this
I
one.
would also, yeah. We actually did uh I think a bit rigorous user study because we invited 8 volunteers, and we do not know them and they do not know our research to make everything really fair. We just invite them, have A/B test. They do not know which system is our proposed systems,
Mm.
and ask them to compare RGB, stereo RGB versus like a point cloud rendering. Turns out the motion sickness, we are really confident about this part. Having online onboard rendering, motion sickness can like be reduced quite a lot. Turns out, data collection, we are slightly slower than RGB teleoperation, and basically we teach the user like volunteer for 3 or 5 minutes, and they can somehow master how to complete our task like the shelf cop and such back tasks, and they can finish our task in within a minute. And in our user study, 6 out of 8 people prefer to use our point cloud rendering, and they think it's just more comfortable. To answer the question, how to train the calibrator first before data collection. And for policy learning data collection, I think I have exact number. I do not remember. It's like 200 around. Yeah. So for example, the cop task is 125, back task is like 150. And this is like a very multimodal initialization. So it's like 260 demonstrations.
Yeah. Yeah, I think this is yeah, I mean this setup probably will just work really well unless the scene is like too dynamic. If let's say there's another guy like teleoperating and you're playing a game against him, like see who catches the ball fastest. Probably you're always a split second, even though like you're
Yeah.
perceived into thinking this is reality, but your reality is like maybe
Yeah.
0.5 seconds later.
Yeah.
But I
So
think so most tasks probably this is fine. I imagine.
yeah, I
Yeah.
think a fast dynamic VR television is still like a very quite interesting engineering problem. I'm not sure, like I haven't seen or let's say the open sourced VR system. They could not like catch ball like naturally randomly. It's just too hard. But it's more like a lot of like robotic engineering need to be done.
Yeah, makes sense.
Sure. Yeah. Yeah, so I mean, what would you say it's some like future work direction, if you were to spend more time on this kind of active vision, which you
Yeah,
would have preferred to do?
yeah.
And
So
another dove to the neck?
yeah, I would say definitely. I think it's more like somehow a minimal humanoid, right? We have an egocentric neck and 2 arms, and we just don't have legs, but we need to move around, have a mobile manipulator. What I'm interested in first thing is I think there's a missing part. We want to dive deeper about this observation representation and action representation. When you move around in let's say we under this end-to-end policy learning paradigm, but when you have like a torso, neck, and mobile base, the first thing is like how would you have a really practical interface to collect data, right? Do you want to have a whole body IK to just control your egocentric camera and 2 ND factors? Or do you want to separate the upper body and the lower body? You just have a joystick. And if you play games like driving cars, joystick is always the most intuitive way to control the mobile base. But when you comes to the humanoid data collection, it might be a different problem. I think you just need to try a lot of different approaches and carefully compare with them. And also comes to the policy learning part, as I mentioned, how would we represent the 3D world if we have stereo RGB cameras. And I think I'm really interested in dive deeper into the machine learning perspective to understand the active perception. Does it actually need nerd's attention? And can you explain the nerd attention when you have like actively, purposefully to search for objects? I think that's what we wanted to do, but we just didn't have enough time to dive deeper. Yeah, and I think the first step for me is just make the mobile meditation platform more practical and more people can just conduct this direction of research.
Cool. And maybe just one more thing, since you're using like Apple Vision Pro, like they do have really good eye tracking as well. So if you want to go even more granular, you could have even tracked that and get even more like granularity to human intention, right? Especially if you're going to lean on human talent.
We wanted to do that. Yeah. We actually had the idea like why not use the eye gaze and you can leverage as another modality to augment your policy. Just unfortunately, Vision Pro actually do not have API for that. They have internal API.
Oh, I see.
I mean, like if we can use it, but we cannot open source it, it's gonna be like miss for research.
Got it. I see. Yeah. Yeah, at this point, I mean, there's so many papers that are using Apple Vision Pro, like that is like, I feel like that's the main market now. It's basically a device for roboticists. Yeah. Okay. Well, but anyway, thank you so much for the presentation. I thought it was like very, you cover all the bases.
Yeah, thanks. Very cool.
Maybe as a final question, like usually we like to ask this, like, are there any like papers you want to give a shout out to? Doesn't have to be like, I don't think there are too many other active vision kind of paper, but any kind of other paper that kind of inspire you or you think was pretty intriguing that you want to give a shout out to?
So I think for the past, let's say 1 or 2 years, I've been really interested in robotic systems, how to make open source robotic system to just lower the barrier of robotic research and make more and more people enjoy robotics. I think 2 papers I really like is TidyBot 2 and UMI. Let's first talk about TidyBot 2. Like actually Jimmy is also on my Vision in Action paper. I think if you look closer to the documentation, GitHub code, everything is like really well organized and everything is like open source and the code is beautiful and the documentation. And man, like he built entire system from like each hardware part. Each part is like, I think there are over 200 or a few hundred parts to assemble the robot and make it really accessible to many users. I think robotics is like a system study. Once we have such ready platform, we can like dive deeper into the scientific problem. Before that, it's just like really hard to get into the core question. I think mobile manipulation of, for example, humanoid or let's say semi-humanoid where you don't have legs, you have upper body, such like a whole body like teleoperation or data collection interface, people might challenge what's the scientific contribution of those projects. That's true, but I think it's still really meaningful. Someone needs to make those platforms available for us before diving into the research problems.
Any idea what is the BOM cost for the TinyBot?
So the TidyBot BOM cost is, I guess, around $5,000 US, but these are all like some very expensive components. For example, from Amazon, they didn't optimize this. And a lot of Chinese startups, industrial startups, they are trying to replicate because it's open source, right? And they have much lower BOM and they can make the platform ready. You don't have to build assemble like a few hundred parts together, and you can just have a mobile manipulator platform ready, and you can start your research.
Yep. Yeah. And of course, Umi, like you mentioned.
As I mentioned, I think just maybe 1 or 2 more sentences to shout out to Umi is like, Umi is a beautiful paper that it combines many details together to make this system work. I mean, like such handheld gripper is nothing new. It's not a new idea, but they can make it capable for like tossing all of those dynamics by manual tasks. If you look at the detail of the paper, there's a lot of detail engineering to make this work. It's not trivial.
Yeah. But I suppose once they have put an active flag, then maybe they can yank out the the wrist camera. maybe.
They will have Eagle Movie very soon, I guess.
Yeah. Okay, but anyway, well, thank you so much, Haoyu. It's been a pleasure having you. Really enjoy your paper, and hopefully, after you go to MIT, I'm sure you have new papers. We'll love to have you again. Yeah, talk about your next one.
Awesome.
Thank you. Thanks for having me.
All right, cool. Thank you so much, Haoyu. All right, Chris, what have you learned?
Yeah, I mean, I think this is really exciting stuff. Active perception in particular is something that's really underexplored And then I get pretty excited about this kind of stuff because it's such an important part of like mobile robots. Because like you can like for any robot that we really deploy, in my opinion, you're gonna have something like this, right? Because it can look around, and that makes so many tasks so much more tractable. But it makes learning harder, so most people don't do it because like you're increasing the variation of where the head can be, and like there's more things changing in every frame. So anyway, I think it's really cool work. Really glad he did it. I don't know.
Yeah.
What did you think?
Yeah, I think so. I mean, like, so because I've tried, like, especially the teleop that I've tried, I focus a lot more on like really remote teleop, like really cross border, where you like. I find that like most people would think of latency as the bottleneck, but oftentimes it's not latency. I think it's just like occlusion and sense of depth, that kind of thing.
Yeah.
So I'm like, always like, can I just move the damn camera? Like, can we just have me move the camera? Like, basically. Precisely, it's just active perception.
Yeah.
I mean, you look at the bar charts that he had, like it's crazy increase. Like
Huge
the jump
difference.
is non-trivial.
Yeah.
Like it's like jump from 50% to like 90%. It's huge jump.
I mean, I always do think, like, I really like this paper. I always do think you shouldn't read too much into plots like that in a paper because, of course, the experiments in the paper are gonna show that his method is bad. But we don't need to look at those to know that like this is a good idea because like this is what we were doing. Like, if you look at our videos, we're constantly moving our heads to understand, even though we're interacting with flat screens here.
Yeah.
To be able to interact with the world, we need to do this, and so it's really cool stuff, in my opinion. I don't know.
Hopefully there'll be more. It would be a pity if this is the only one. Like, because I don't think I've found any other paper that actually have a knack there. So
yeah, right.
So much focus on Activision. Yeah, hopefully he can continue something along this line when he go to MIT. Anyway, okay, cool. I guess until the next one, Chris. All right, see ya.
See ya.